This presentation is based on Lab 13, Do the Wave, which explores extending transverse wave and their characteristics. The main purpose of this experiment is to compute the string linear mass density using both physics models and equations and fitting methods, such as analyzing a graph. This linear mass density is represented with the Greek letter mu. Yet, we will also identify how the fundamental frequency and harmonic frequencies vary with the tension different for masses, and how the wave velocity is related to the tension force of the restoring force of a string. For this experiment, we obtained two different values for the linear mass density. For the first half of the experiment, we got an average value of 0.2719 grams per meter. For the second half of the experiment, using a power series fitting graph, we got a linear mass density of 0.2723 grams per meter. Those values were very close to each other. In addition, for our fitting graph, we got a constant of 60.6 and an n value of about 0.5. This n represents the number of the exponent in the fit line equation for the power series trendline, but this will be analyzed further during data analysis. Before we jump to the experiment setup, there are a few wave properties that are important to understand before starting the experiment. Those are the amplitude, wavelength, frequency, and speed. The amplitude is how high a wave oscillates up and down, and it is shown by the pink arrow in this graph. The wavelength is the distance from cross to cross, and it is represented by the green arrow in this picture. The frequency and how fast the wave oscillates, and this is what we will be doing in the experiment. And the speed is how much distance is covered in a period of time. Knowing this terminology, we make our data collection a little bit easier. The first step for this experiment was to connect the function generator to the wave driver and set up a ring stand with a pulley. In the following video, you will see that the black cable was connected to the ground port and the red cable to the low resistance port. This means that the current through the wave driver was high since the resistance was low. In the video, the knob that we are manipulating controls the frequency, and the knob next to it to the right controls the amplitude. Regarding the right stand with the pulley, we make sure that it was tight and horizontal, because then we attach one end of a 2-meter long string over the pulley and attach the other end to the wave driver. It is important to have the wave driver and the ring stand on separate tables, maintaining a constant horizontal length of 2 meters between both objects. In the picture on the top right, you can see the complete setup, including the placement of the wave driver and ring stand, with the red light simulating the length of the string. During this part of the setup, it's also important to have the amplitude all the way down, therefore the string is not moving or vibrating. It is also important to remove all the belongings from the table, because the wave driver, when oscillating at certain frequencies, will cause strong vibrations. These vibrations can shake the table and cause the belongings to move around, but it could also affect the experiments and lead to inaccurate measurements. Therefore, by clearing the table, we are trying to minimize external interference and damage to any belongings. Continuing with the experiments, once we make sure that our string was horizontal, we tie some knots in the hanging string of the pulley to then attach the first mass to it. You can use a marker to help you tie an open loop knot to easily change the masses on the hanging string in between the data collection. Also, we took a piece of tape and placed it at the bottom of the string stand and the wave driver. This helped us make sure that the objects stay in place to the experiment of if we needed to readjust the length of 2 meters. Now, we started to take measurements. We first hooked the 100-gram mass to the knot, turned the amplitude halfway up, and started increasing the frequency from 20 Hz until we found the second, third, and fourth harmonic frequencies, and we recorded those measurements. We repeated this process for the other masses. We used 200 grams, 150, and 50 grams. The standing wave that you should observe should look like those on the picture at the bottom, with clear notes and antinodes. Remember that we are counting the notes at each end, therefore, the second harmonic should have 3 notes, the third harmonic 4 notes, and so on. Because of the relationship between frequency and velocity, we could predict a starting frequency for the next harmonic. Moreover, we tested that we were looking at standing waves by checking the notes and antinodes. The nodes, as circled in the picture, represent that there is a stationary point of no motion. On the other hand, the antinodes represent the maximum amplitude of the wave as being pointed by the arrow. We were also following the principle that standing waves should appear stationary on the string. In the following video, you will see how the string kept moving fast and there were no clear notes on antinodes yet, so we still needed to increase or decrease the frequency to find a steady and big amplitude. Some things to keep in mind during this experiment is to make sure that the length stays constant and that the mass being used does not exceed 300 grams. Before plugging in numbers, we rearrange the wave equation to find the linear mass density, it being equal to the force tension over velocity squared. We also review the second half of this equation to solve for velocity and wavelength by using the relationship between velocity, frequency, and wavelength. In addition, we previously collected some data for the harmonic frequencies, and we will find the fundamental frequency by using this formula and averaging all of the frequencies together. Lastly, to solve for mu, we need the tension force. By drawing a free body diagram, we identify that the tension force will be equal to the mass in kilograms times gravity.
We aim to determine the mass density of a vibrating string by analyzing standing waves at different harmonic frequencies. To create the tension in the string, we use different masses over a pulley, which applied the force to gravity. We then used a wave driver to generate vibrations and measure the second, third, and fourth harmonic frequencies, since the fundamental frequency is difficult to measure directly. We estimated it using the relationship of the vibrating string and the wavelength when the wave is vibrating at its fundamental frequency. In our case, the string supports exactly half of a full wave. Since one wavelength consists of 2 halves and only half of the wave fits along the string, we use L equals lambda divided by 2. The length of our string was a constant 2 meters for every harmonic. After calculating the fundamental wavelength was 4 meters. Using this wavelength and our estimated value of F1, we calculated the wave speed with the equation V equals F1 times lambda 1. After solving for V, we were then able to use the equation to solve for linear mass density, which was 0.2675 grams per meter. This method allowed us to experimentally confirm how tension and wave behavior relates to the physical properties of the string. To analyze the relationship between wave velocity and tension, we plotted the wave speed against tension and fit the data with the power function of the form V equals A times T to the nth power. The equation from our data was V equals 60.6 squared by 0.503. The exponent n should theoretically be 0.5, since the wave speed on a string is defined by the equation that velocity is equal to the square root of tension divided by mu. Our fitted value of n equals 0.503 is extremely close to the expected 0.5. This indicates that our data is consistent and reliable. In our equation, the constant a equals 60.6, and that represents 1 over the square root of mu, meaning that mu equals 1 divided by a squared. Substituting our value of a, we get mu equals 1 over 60.6 squared, equaling to 0.2723 grams per meter, which is close to matching our average experimental value of 0.2719 grams per meter. The variable n in the power series fit is especially useful to assess the accuracy of data. If n is not close to 0.5, there is likely an error in the measurements. In our experiment, the goal was to find the string linear mass density by using and rearranging the wave speed equation by fitting. We determined the linear mass density of a string by investigating how the frequency of standing transverse waves changes with varying tension. Since mu and tension directly affect the wave speed and frequency, we measure the frequencies of the second, third, and fourth harmonics and use them to estimate the first harmonic frequency. We then used it to calculate wave speed, then verified the results by plotting a wave velocity against tension and fit the data with the power equation. The results show that the wave speed increases with the square root of tension. This not only supports our experimental value of mu, but also demonstrates how wave behavior on a string can reveal important physical properties through harmonic analysis. In conclusion, the theoretical predictions that were calculated in two separate ways were accurate with the results found.